All right, so let's continue our study of gases. In this video, there's two main topics I want to kind of touch on. The first is kinetic molecular theory, and the second is pressure. So let's first start with our KMT. So let's go ahead and write down this definition, but the kinetic molecular theory kind of just describes the behavior of an ideal gas or ideal gases. Okay, so let's look at the word ideal. Ideal means to be perfect. So when we say that the gases are behaving ideally, they are following four assumptions for us. And those four assumptions are the four assumptions of KMT. So the first one is that gas particles move in constant, rapid, straight line motion. Okay, you may want to pause and write each one of these down. The second assumption is that gas particles have no volume. That's why we can compress a gas. Obviously, a real gas would have some volume, even though it's really, really small, it would still have some volume. But when a gas behaves ideally, we just consider their particles to have no volume. Moving on to the third assumption. Gas particles do not attract or repel each other. So there's no forces happening in between them unless they run into each other. And then the final assumption here is that gas particles have elastic collisions. So you may not remember this from physics, so I do have a definition for you. The elastic collisions mean that the kinetic energy is being transferred between the particles without any loss. So the particles will just keep moving forever. So I do have a model that I want to look at that describes this, but before, I just want to make sure that we do take this one note here, that real gases follow these assumptions under ideal conditions, but under extreme conditions of temperature and pressure, so really high temperatures or really low temperatures, high pressure or low pressure, gases don't behave in an ideal way. So let's just write this down and then we'll go to our model. Alright, so we're at our model, and what I want you to kind of see here is we are assuming that these here are gas particles and they are behaving ideally. And what that means is that they are moving in straight lines, they're in constant motion, and when they do run into each other, that they no energy is lost there. Eventually you would assume that these would eventually bump into each other enough and slow down and all stop. But that's not what we see in an ideal gas. What we see is that these collisions are perfectly elastic. That means that there is no energy loss, and they will just keep bouncing off of each other forever. And this is how an ideal gas would then behave, is in this rapid motion like this. Okay, so that pretty much sums up KMT for right now. So what I want to move on to is the idea of pressure. So pressure is the force the gas particles exert on an object because of their collisions with that object. I do have a model that I want to kind of go to and show and that we can look at. So let's go to our model. So here's our model, and when we're looking at gas pressure and we're talking about collisions, we're really thinking about two different ways that the gas can change. Either the gas particles hit the outside of the object more often, or that means just more times, or harder, so they're hitting it faster and faster. So if we look here, here's our pressure here. Right now it's at about 0.20 atmospheres. So if we increase how often they can hit the outside and how fast they're moving, so we increase the temperature here and they're going to move a lot faster. And you can see that they're hitting the outside of this object faster. And you can see that the pressure is increasing because of that. So since they're hitting the box more often and faster, that increases the pressure. If we slow it down and we don't allow the gas particles to hit as often, you can see they're not hitting as often and they're moving a lot slower. The pressure has gone down. So back to our notes. What you may not realize is that we all live at the bottom of an ocean of air. There's air all around us, and we feel this pressure from this air. You may take it for granted because you've lived with it for your entire life, but it's still there, and we have a name for it. It's called atmospheric pressure. This is the pressure from the Earth's atmosphere exerted on objects like ourselves, and we feel it every day. There will be some demos that we'll do in class to show how much pressure is applied to us every day from this atmospheric pressure. And so we'll take a look at that after we view this video. One more idea that I kind of want to look at is that the higher you go up in Earth's atmosphere, the lower the pressure is going to be. So if we look here, Denver is quite a bit higher in elevation than we are, so there's going to be less particles here. That means there's going to be less chance for the particles to hit your body and apply less pressure. If you're down here with St. Louis air, a lot more air particles, a lot more of a chance for them to hit your body and apply some type of pressure. So moving on, there was a question that I asked before last time with the temperature is how high could a temperature go? So we want to look at those same type of limits with pressure. So how high can pressure go? Is there an upper limit to the pressure? And as long as we can apply force, I don't see why we couldn't have a higher and higher pressure. But like what we saw with temperature, there is going to be a lower limit. So how low can pressure go? Is there a lower limit? And we're going to have to say yes. If the particles cannot hit the object with any speed or at all, that means that there's no particles whatsoever. Then there's not going to be any pressure whatsoever. And we have a definition for that. That's called a vacuum. So a vacuum is an environment with no air pressure because there is no gas. That's how we are going to define a vacuum. So here are the units that we measure pressure in. So you might want to take a moment now and just write all these down. So these are all our units for measuring pressure, and we'll talk more about these individually in class, but I just want you to just kind of write them down now. Also, this idea of a standard temperature and pressure, STP. So these are the conditions that scientists all agree upon, that this is the standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. Alright, so let's look at measuring pressure. One of the ways that we can measure pressure is with a manometer. So with a manometer, you have a flask with some type of gas in there at some type of pressure. You also have here, this is mercury. And then you have an open end here where the atmospheric pressure is pushing in. So if we say the atmospheric pressure has a pressure of 750 millimeters of mercury, which is a unit of pressure, and we look at this particular one here, we can see that these two levels are equal. So the pressure inside of this flask, the pressure of this gas, is equal to the room pressure, which is 750 millimeters of mercury. So what happens if there's a difference in the pressure? So we see it here and here. Well, if the pressure inside of the flask is more, it can push further and harder on the mercury, forcing the mercury up the tube and pushing the atmospheric air out. So that means that the pressure inside of this flask has to be greater than the pressure in the room because it's able to push further down on the mercury. So to figure out the pressure inside this gas, we just simply take the pressure of the room plus the difference here in their height, so 300 millimeters, and we get 1050 millimeters of mercury. That would be the pressure inside the gas. Now if we look at this example here, the room pressure is going to be more and can push the mercury further down the tube and pushing it up towards the actual gas here. So the gas inside of this flask is actually at a lower pressure than the gas inside the room. So we would subtract this difference here. So we would have 750, that's the pressure of the room, and minus this height, because that's how much further it can push it down. So we get 650 millimeters of mercury. Now that is going to be the pressure of this gas here. This is something that you're going to be practicing in class, so please, if you do have questions, make sure that you're writing them down and then that you bring them in to class, because this is something that you're going to be responsible for doing when we meet back into class. So there's just one more thing that I want to do and cover in this video, and that is just converting. We had all those different units of pressure, and sometimes we have to convert from one unit of pressure to another unit of pressure. So I just want to do one quick example. We'll do more in class. If you have questions, just like if you have questions about this, please write those questions down, email them to me, or bring them into class when we meet. So here's all our different units, and you can see that each one of these is equal to the next. So how are we going to convert from one unit to another unit of pressure? So here's our first question that I kind of want to just ask here. So if we have 16.5 psi, psi means pounds per square inch, I want to know how many millimeters of mercury is that? Well, the first thing that I want you to do is put whatever you're given, the 16.5 psi in this case, here in this part of the box. So after you make this little box, you put the 16.5 psi there, and you'll put just a 1 underneath it. You always just put a 1 underneath whatever you are given. So it doesn't matter what you have here, what unit you have here, as long as this is what's given to you, you put a 1 beneath it. Then we want to go to millimeters of mercury. So you want to find, well, what number are we going to use up here? So millimeters of mercury, we are going to use 760. So that's what's going to go here on top, because that's what we want to convert to. So whatever we want to convert to will go on top. Then we have to find whatever matches the unit of the given and its number. So we have psi, so we're looking for psi here. We have psi right here. 14.7 psi would go right underneath here. All right, so we want to know, well, what does this equal? So we are going to multiply across the top. So I'm going to get my calculator here. So we have 16.5 times 760 equals, and I get 12,540. We also are going to multiply across the bottom, so I need my bar still here. And we are multiplying across the bottom here, and that's going to be pretty easy. I don't really need a calculator. You just take 1 times 14.7. That's going to be 14.7. And then what you do is you divide these two numbers here. You take your 12,540 divided by 14.7, and you get your answer here. So equals 853 millimeters of mercury. So again, just to review this real quick, because I know a lot of people have trouble with the conversions. Whatever we are given, we put in this top box here, over 1. Whatever unit we want, we find that number here that matches that unit, 760 millimeters of mercury. That's what we put here. Whatever matches this unit, the given unit, and its conversion, which is 14.7 psi for this case here, multiply across the top, multiply across the bottom, and then divide these two, and you will end up with your answer. So this is something that we're going to practice in class. Please bring any questions that you have. The two main things that I want you to make sure that you understand through this video is that we have the 4 assumptions of KMT, and also pressure and how to measure it, how to convert it, and what it is. Thank you so much, and I'll see you in class.